You think you understand the universe. You think it's just stars and galaxies scattered across some vast emptiness, expanding outward like dots on a balloon. Fine, comfortable, safe. But let me ask you something that should bother you. If space is expanding, what is it expanding into? If everything started from a single point, what existed before that point? What happens when a star collapses so completely that not even light can escape? Most people have never really thought about this. They hear Big Bang and nod. They hear black hole and picture some cosmic drain sucking in spaceships. That's not an answer. That's just repeating words you've heard in documentaries. But when you really ask what's happening out there, when you dig into the mathematics, when you trace the equations to their logical conclusions, you discover something so strange, so fundamentally disturbing, that it changes everything you think you know about reality itself. The universe isn't just big. It's not just old. It's structured in ways that break your brain if you look carefully enough. Time doesn't flow the same everywhere. Space itself can curve so completely that directions stop making sense. And somewhere out there, right now, stars are collapsing into objects so extreme that the mathematics predict something impossible. Regions where time literally stops from your perspective while continuing normally for someone else. Let me show you what I mean. If you've never questioned this before, you're not alone. But now that you're seeing it, there's no going back. Once you understand what's really happening in the cosmos, you'll see it everywhere. In every photograph of distant galaxies, in every news story about gravitational waves, in the GPS satellite that told you where to turn this morning, and you'll wonder why most people still don't get it. Start with something simple, something you can observe. In the 1920s, astronomers pointed their telescopes at distant galaxies and measured the light coming from them. They noticed something peculiar. The light wasn't quite the right color. It was shifted toward red. Now you might think light changes color all the time, sunset, neon signs, nothing special, but this was different. The shift followed a pattern. The farther away the galaxy, the more its light was red shifted. Not a little, a lot. What causes this? Motion. When something moves away from you, its light gets stretched. Like the sound from an ambulance speeding away, the pitch drops. Same thing with light. Motion stretches the wavelength, makes it redder. Edwin Hubble measured this precisely. Galaxy after galaxy all moving away. And the farther they were, the faster they were receding. This wasn't random motion. This was the universe itself expanding, space stretching. Every point moving away from every other point. Not because galaxies are flying through space, but because space itself is growing. Think about that for a second. You're not sitting in a fixed location watching things move past. The fabric of reality underneath you is stretching right now, every second. The distance between you and a galaxy 1 billion light years away is getting larger. Not because either of you moved, but because the space between you expanded. Now, here's where it gets uncomfortable. If space is expanding now, run time backward. Galaxies get closer. Space compresses. Keep going, further back, further. Until when? Until everything, every galaxy, every star, every atom was in the same place. Compressed into something unimaginably small and dense. That moment, that beginning, we call it the Big Bang. Not an explosion in space. The explosion of space itself. The moment when distance meant nothing because there was no distance. The moment when time itself began because time is part of space and space didn't exist yet. This sounds like philosophy. It's not. It's measurement. We can see the afterglow of that moment. The cosmic microwave background radiation, light from when the universe was 380,000 years old, still traveling toward us from every direction. We've mapped it, measured its temperature fluctuations to millionths of a degree. The data matches the predictions with terrifying precision. But knowing the universe began doesn't tell you how it ends. And that question depends on one thing: gravity. Everything in the universe has mass. Mass creates gravity. Gravity pulls. Even though space is expanding, even though galaxies are flying apart, gravity is working against it, trying to pull everything back together. It's like throwing a ball upward. The ball rises, but gravity pulls it back. Whether it comes back down depends on how fast you threw it. Throw it slowly. Gravity wins. The ball rises, slows, stops, falls back. Throw it faster, at exactly escape velocity, and the ball just barely escapes. It keeps rising forever, but its speed approaches zero at infinity. Throw it even faster and it escapes easily, keeps rising, never comes back. The universe is the same. Everything depends on the balance. How fast is space expanding versus how hard is gravity pulling back? This gives us three possibilities. Three ways the story could end. The first possibility: space expands too fast. Gravity can't slow it enough. The universe expands forever. Galaxies race apart until they're so far that light from one can never reach another. Stars burn out, everything goes cold, dark, empty. The universe doesn't end in drama, it just fades. Gets colder and more empty until nothing interesting can ever happen again. Forever. The second possibility: space expands at exactly the critical speed. Gravity pulls back just hard enough to slow the expansion but not stop it. The universe keeps expanding forever but slower and slower. At infinite time, the expansion rate approaches zero. Perfectly balanced, the flat universe. The third possibility: space doesn't expand fast enough. Gravity is too strong. The expansion slows, stops, reverses. Galaxies stop receding, then start approaching. Space contracts, everything gets closer, denser, hotter. Think of the Big Bang in reverse. Eventually, everything collapses back into a single point. A big crunch. The opposite of the Big Bang. The universe that began in fire ends in fire. Now, here's where it gets even stranger. You're realizing that everything you thought you knew was incomplete. That feeling, that mixture of excitement and frustration, that's growth. That's your brain rewiring. How many other things do you accept without questioning? What else is hiding in plain sight? While physicists were thinking about the universe expanding or contracting, someone realized something. If the whole universe can collapse, what about individual objects? What about stars? Stars are remarkably stable. For millions of years, billions even. They burn hydrogen. Fusion reactions in the core release energy. Radiation pressure pushes outward. This balances gravity trying to crush the star inward. Equilibrium. But nothing lasts forever. Eventually the fuel runs out, hydrogen is exhausted. Fusion slows, then stops. The outward pressure disappears. And gravity wins. For small stars, stars like our sun, this is relatively gentle. The star cools, contracts, becomes a white dwarf, an Earth-sized ember made of compressed matter. Hot at first, but cooling over trillions of years. Eventually becoming a cold, dark sphere. A stellar corpse. But for massive stars, something different happens. Something violent. When fusion stops in a massive star, the collapse is catastrophic. The core implodes in seconds. Electrons are squeezed into protons. They combine, forming neutrons. The core becomes a neutron star, a ball of pure nuclear matter, the size of a city but with the mass of the sun. The density is beyond comprehension. A teaspoon of neutron star matter weighs as much as a mountain. Gravity at the surface is so strong that if you dropped something from 1 meter up, it would hit the surface at a significant fraction of the speed of light. But neutron stars have a limit, about 1.5 solar masses, the Chandrasekhar limit. Beyond that, even neutron pressure can't hold the star up. Then what? The collapse continues. And this is where the mathematics predicts something that should break your brain. Karl Schwarzschild found a solution to Einstein's equations back in 1916, during World War I, while serving on the Russian front. He was calculating what happens to space and time near a massive, dense object, and he found a critical radius, a boundary. For any given mass, there's a size below which the equations predict something bizarre, a point where the mathematics says time stops, where space curves back on itself completely. For the Sun, this critical radius is about 3 kilometers across. For Earth, it's about 9 millimeters, the size of a marble. Normal objects are nowhere near this limit. Their actual size is much larger than their Schwarzschild radius. But if you could somehow squeeze the Sun down to 3 kilometers across, or Earth down to a marble, you'd hit this boundary, this critical circumference, where the math stops making sense, where something very strange happens. An object compressed below its Schwarzschild radius. A collapsed star. That's what physicists called these things in the 1960s. Some people said frozen star, others said black star, because no light escapes from them. Whatever you called it, the predictions were disturbing. Let me describe a thought experiment. Forget the mathematics for a moment. Just imagine this scenario. A massive star is collapsing. Its core is imploding. Gravity is crushing it smaller and smaller. And imagine someone, an observer, standing on the surface of this collapsing star, riding it down, falling inward with it. Now imagine you're far away, safe, watching through a telescope. What do you see? At first, nothing unusual. The star shrinks, gets smaller, denser. The observer on the surface falls inward. Light from the surface travels to your telescope. You see him there. Maybe he's waving, sending light signals. But as the star approaches the critical size, the Schwarzschild radius, something strange starts happening. The light reaching you from the surface changes. It gets redder, dimmer. This is gravitational redshift. Light climbing out of a strong gravitational field loses energy. Its wavelength stretches. It shifts toward the red. The stronger the gravity, the more the light is red-shifted. And as the star approaches the critical radius, the gravitational redshift becomes extreme. But that's not all. Time itself is affected. The observer's movements appear to slow down. He waves his arm. But from your perspective, far away, the motion takes longer than it should, and longer, and longer. To him, nothing is different. He's waving at normal speed. His watch ticks normally. But the light carrying that information to you is being stretched by gravity. Delayed, we're about to connect everything. But before we do, ask yourself, are you the kind of person who actually follows through? Who takes knowledge and does something with it? Because what comes next isn't just information. It's a lens that will change how you see everything, and you can't unsee it. As the star gets closer and closer to the critical size, the effects become more extreme. The observer moves slower and slower from your perspective. His light gets redder and redder, dimmer and dimmer. Finally, as the star reaches the Schwarzschild radius, something impossible happens. From your perspective, the observer stops completely, freezes in place. Like a photograph, his image is stuck there at the boundary, forever falling but never quite crossing. Time has stopped for him, at least from your point of view. His light is so red-shifted, it's essentially invisible. He's frozen at the edge of this collapsed star for all eternity. This is why some people called it a frozen star. From the outside looking in, nothing can ever cross that boundary. Everything just slows down and freezes there. But here's the really mind-bending part. What about the observer's perspective? What does he experience? Nothing. Nothing at all. From his point of view, time passes normally. He doesn't slow down. He doesn't see anything unusual. The critical boundary, the Schwarzschild radius, he passes right through it. No warning, no sign, no jolt or discontinuity. Just smooth, continuous motion inward. To him, it takes maybe a few seconds, a minute, some finite time. He crosses the boundary without even noticing. But once he's crossed, something has changed. He tries to send a signal out, a radio transmission, a light beam, anything, and it doesn't work. Not because the signal is blocked, but because space itself is so curved that every direction is inward. There is no outward anymore. All paths, every possible trajectory, lead deeper into the star, toward the center. He's trapped. Can't communicate, can't escape, can't signal for help. And from his perspective, he just keeps falling, eventually reaching the center where tidal forces become infinite and everything is crushed. The math breaks down there. We don't know what really happens. From outside, you see him frozen forever at the boundary. From inside, he fell through in finite time and is doomed. Both descriptions are true. They're just two different perspectives on the same physical reality, because time itself flows differently in different places. Near strong gravity, time runs slower relative to distant observers. And at the Schwarzschild radius, from an outside perspective, time essentially stops. This might sound like science fiction. It's not. Time really does flow at different rates in different gravitational fields. We've measured it. Your head ages faster than your feet right now. Not much, but measurably. Your head is slightly farther from Earth's center. Gravity is slightly weaker there. And time runs slightly faster. Over your entire lifetime, your head will age about 90 billionths of a second more than your feet. You can't feel it, but it's real. In 1960, physicists Robert Pound and Glenn Repka did a beautiful experiment at Harvard. They took gamma-ray photons and dropped them 5 meters from the top of a tower to the bottom. They measured the frequency when the photons arrived. The frequency had changed, shifted, because the photons fell from a region where time runs slightly faster to a region where time runs slightly slower. The shift was tiny, 1 part in 1,000 trillion. But they measured it, proved it. Time really does flow at different rates. Near a neutron star, the effect is dramatic. Time at the surface runs maybe half as fast as time far away. An hour there is 2 hours for distant observers. And near the Schwarzschild radius of a collapsed star, time from a distant observer's perspective essentially stops. An hour for the falling observer might correspond to billions of years. Infinity, technically, for distant observers. This is why the falling observer appears frozen. He's not frozen from his own perspective. But time is running so differently for him that from your point of view, he might as well be stopped. Earth's core is younger than its surface. About 5 years younger. Because time runs slower down there in Earth's stronger gravity. Over 4 or 5 billion years, that adds up. This isn't speculation. It's not theory in the sense of maybe it's true. It's measured, confirmed, as real as anything in physics. So now what? You've just spent the last several minutes fundamentally changing how you understand reality. That's not nothing. That's rare. Most people never have this experience. The question is, will you remember this tomorrow, next week, or will it fade like everything else you've learned and forgotten? There's a way to make sure it sticks. There's a way to prove to yourself that this mattered. So let's bring this all together. The universe is expanding, has been since the beginning. We can measure it in the redshift of distant galaxies. Run time backward and everything collapses to a point. The Big Bang. Run it forward and maybe space expands forever, growing cold and empty, or maybe it collapses back. We don't know yet. Individual stars collapse too. Small ones become white dwarfs. Massive ones become neutron stars. And the most massive, those that exceed the limits, collapse completely, past the Schwarzschild radius, into regions where light cannot escape, where time stops from the outside but continues inside, where space curves so completely that all directions lead inward. These aren't mathematical curiosities. They're real objects. We've detected them indirectly. Watched stars orbit invisible companions too massive to be neutron stars. Measured gravitational waves from them merging. The equations predicted all of this decades before we confirmed it. And this process, this avalanche of discoveries, started with Hubble figuring out the universe was expanding by measuring redshifts in the 1920s. Then Einstein's equations predicting how space and time curve. Then Schwarzschild finding that critical radius in 1916. Then Chandrasekhar calculating the limit beyond which neutron stars cannot exist. Then Pound and Repka proving time dilation in 1960. Each discovery building on the last. Each new insight opening doors to more insights. That's how science works. That's the avalanche that's been going on for over a century. And we're still avalanching along at high speed. The universe isn't just big. It's not just old. It's structured in ways that challenge everything you think you know about reality. Time bends. Space expands. Stars collapse into darkness. Regions exist where time itself stops from one perspective while continuing from another. These aren't contradictions. They're both true. That's the nature of it. When you really stop and think about what the equations are saying, the universe is far stranger than it appears. Not simpler, more complex, more beautiful, more disturbing. And the fact that we can understand it, that we can measure it, test it, use it to make predictions that come true, that's the beauty of physics. Not comfort, not simplicity. Truth. If you made it this far, you're part of a small group. The group that doesn't settle for simple answers. The group that wants to understand, not just know. People who think like this, they find each other. They recognize each other. They build on each other's understanding. That's how the avalanche continues. That's how we keep discovering, not alone, together.